Hello, and welcome to this evaluation report on the KAIST in-house C2 project, Computer Science for Continuous Data in Parallel. We start by sharing the screen. Let's dive right in. I'm going to start by recalling the progress from theory to practice in general, and for the particular case of parallel computing. Then I will recall the difference between hardware and mathematical data types and how that leads to programming errors, which we want to prevent for the case of continuous data processing. Then I will remind you of Picard iterations and why and how we want to accelerate them using parallel processing and which kind of hardware we have explored so far. A multi-core CPU, a graphics processing unit, field programmable gate array, and a new anti-von Neumann architecture, which we call XpLUTo. Finally, I'm going to wrap up, recalling formal achievements, work in progress, and our future plans. So let's start with progress from theory to practice. And one early example is Alan Turing, who in 1936 published his famous paper introducing a mathematical model of a digital computer which did not exist at that time. In fact, it took 5 years until Konrad Zuse managed to become such a computer operational. Another example is Peter Shor, who in 1994 developed a quantum algorithm for factoring integers in polynomial time. And since then, and because of that, engineers and physicists have kept trying to actually realize these quantum computers. Now, I myself graduated in 2002 from Paderborn University as part of the maybe worldwide most famous center on the theory of parallel computing. My PhD advisor, Friedhelm Meyer auf der Heide, actually visited KAIST and gave a lecture in 2017. So this is the background that I'm applying here in this current project. And applying this to continuous data types. So let's recall the difference between hardware and mathematical data types and how that leads to programming errors at the example of an old computer game called Civilization, where the human user, governs a country through its progress through the ages, and the neighboring countries are governed by the non-player character using some basic parameters. For example, India is governed by Gandhi, who has a very low aggression parameter of 1. And one rule of the game is that during the play, when the country develops democracy, its aggression decreases. It decreases by 2, and the intention of the program, of course, was to make it decrease, but actually on a data type byte, subtracting 2 from a value of 1 results in a wraparound value 255, making Gandhi wage war against its neighboring countries. Now that's of course all fun, but the underlying cause is of this program error is the difference between hardware and mathematical data types. Our research is about continuous data types, and here you see an example of the famous Intel 8087 coprocessor from 1985 for accelerating floating point processing. Floating point are, of course, the hardware data type for real numbers. So hardware data type byte is different from mathematical data type integer, but nowadays programming language support the mathematical data type integer with something, for example, called long int by simulating it in software. And floating point numbers are different from real numbers, which also result in programming errors, for example, in the Ariane 5 maiden flight or the Sleipner A oil platform design. And our research is about simulating mathematical real numbers with a software data type called real number, for example, using the IRAM C++ library. Now proceeding from single real numbers to real number functions, for example, continuously differentiable or integrable functions, there is no corresponding hardware data type because it's going to be very slow, and our goal is to provide such a data type and to make it fast using parallel processing hardware. So computer science for continuous data is about functions, and the core operations we want to support and accelerate include differentiation, integration, and maximization. And I'm applying the background from parallel computing, but there the discrete realm, and applying that to the continuous setting. And to this end, we're focusing on accelerating and parallelizing Picard iterations. Picard iterations are about continuous function, but they are not named after this Picard, but after Charles-Émile Picard, French mathematician who developed this technique in order to prove the existence and to construct solutions to difficult, complicated problems, such as, for example, the Navier-Stokes equation underlying one of the Millennium problems. Now here you see a prototype example of such a Navier-Stokes, of such a Picard iteration. It starts with an approximate solution Fk, and then applies a simple operator, and then integral, and then prove that this iteration gives a better approximation Fk plus 1, which in the end converges to the solution. This is nowadays a well-known technique in pure mathematics, but applying it in numerics is usually deprecated because of its slow performance, at least when applied sequentially. But recall, our purpose is to use hardware parallel acceleration. So here's are some examples of Picard iterations. This is a Picard iteration for the exponential function, and more generally, we have a continuous function, then we discretize it using samples, and in order to approximate the function up to 2 to the minus n, if the function is, let's say, Hölder continuous, then this takes exponentially many samples of linearly many bits, and this is why it's so slow sequentially. But when turned into these samples integraled into a Riemann sum, then this is a case of a prefix sum problem, which is well studied in the theory of discrete parallel processing. There it is well known to have Boolean circuits, which are not too large in terms of the number of gates, but which are very shallow, small logarithmic depth, which amounts to parallel runtime, which in our case boils down to n log n, so very fast, at least in theory. So how can we translate that theory to practice in the best way, and which hardware should we use? This is a non-trivial question, since the Boolean circuits are pretty complicated, as you see here. So we're going to explore different hardware options to turn that into fast practice. 4 hardware options. First one is a multi-core CPU. Second is a graphic processing unit. Third, a field programmable gate array. And here you see an example for Zen 3 CPU, which already has 8 cores that can be operated in parallel to accelerate processing. Graphic processing units have even more cores. Here, this one has 256 cores. This is one of them. And FPGA have even more parallel processing units called configurable logic blocks, CLBs. Specifically, current CPUs have maybe up to 20 or more cores, which are pretty powerful. Each one has its own control unit. Graphic processing units have more cores, but few processing units, control units. So this is a case of single instruction, multiple data. And FPGA can have up to millions of configurable logic block, but each configurable logic block is even more simple in its computational power. Then there's also the issue of memory. So CPU and GPU have gigabytes of memory, whereas FPGA have only 100 millions of bits of memory. Which one is suited best? And Sehun Park has pursued this question, implemented the prefix sum for the Picard iteration on multi-core Intel i7 CPU. And here you see how the running time grows with the precision parameter M, but also how the runtime decreases using more of its cores, up to 16 cores in this case. He also has performed this investigation on a graphic processing unit. Here, one needs more, like up to 200 cores to obtain the same runtime as with a multi-core CPU. And then there's a kind of stagnation. Employing even more cores does not give further acceleration. This is the work of Sehun. We already also tried to implement that on a expensive FPGA board that we were able to purchase with funding from this project. But it turns out that FPGAs seem more tailored towards pipelining than towards the massive parallelism underlying the Boolean circuits. But following Thomas Edison, there must be a better way to do it, and we tried to find this better way. And to this end, we have explored in-memory processing, more precisely, inverse to the traditional von Neumann architecture. Traditional von Neumann architecture moves the data to the processing unit and then stores the result back in memory. And this you can see here. And our inverse architecture, which we call XpLUTo, conversely moves the processing unit or the instructions to the memory in form of small lookup tables. And this is the work of Nguyen, intern at KAIST, originally from Ho Chi Minh University of Technology. So to summarize, we have published in 2 international conference reviewed proceedings. We have 3 technical reports, preprints, and we collaborate with Dr. Alexander Stoimenov on computational knot theory, and we're part of the EU Horizon Marie Curie exchange program. Here's the webpage of our project. Implementations in C++ are available on GitHub, and we have a YouTube channel where we collect both courses and research presentations. In future, we want to turn the reports and the technical reports into publications, starting with Sehun presenting at the conference at Kyoto University as part of the EU project. He will then proceed to implement and evaluate further Picard iterations, make them available as new operation in IRM with C++ interface, publish that, and then graduate. In the long run, we'll continue bridging the gap from theory to practice and turn IRM into a computer analysis system. So that's the end of my presentation, and I'm available for your question. Thank you very much.